worked with radicals before, simplifying radicals, even in geometry, you guys would have seen this at first in Algebra 1, and then you would have seen it again in geometry. Not necessarily with coefficients, but you guys would have, like with the distance formula and other things in geometry, you guys would have simplified radicals. So we're taking that idea and extending it a little bit, and revisiting some stuff from Algebra 1 that you guys have probably seen before. A little bit of vocabulary before we get started. So we have three main vocabulary words for this unit. The first one is radical expression. So any expression that involves this symbol, which we call a radical. So this root or radical symbol is illustrated right there. Whatever is inside is called the radicand. So anything that's inside the radical symbol itself is called a radicand. The index is the little number that's kind of up here in the corner of the radical symbol to tell you which root you're taking. So it could be a cube root, a fourth root, fifth root. This little number right here is called the index. It tells you what kind of root it is. Now, you guys have heard of square roots before, right? When we draw a square root, it looks like this. Do you see a number written right there? No. However, you guys do need to be aware that it does have an index of 2. A square root has an index of 2, we just don't write it, right? There's no such thing as an index of 1. The indices start at 2, we just don't write it, and that's considered a square root. Once we start actually writing indices, it starts with a 3 and then goes up from there. So you guys do need to remember that a square root has an index of 2. That's left under. Now, the first thing in this lesson, we're going to be talking about simplifying radicals and then multiplying and dividing them. We're going to leave add subtract for our next lesson in this unit. So the first thing you guys need to understand is this idea right here. So in order to cancel an actual radical, you have to have the power and the index match. That helps them cancel. So when we've seen things like this, the square root of 2x equals 4, right? What's the first thing you do to solve this? You want to get rid of the square root, right? How have you been trained to do that? What do you do to get rid of the square root? You square. The reason why is because a square, whether it's inside or outside of the radical, doesn't matter. If a power matches the index, which I already told you the index of the square root is 2, if those two match, then they both cancel each other, leaving you with just the radicand. Okay? So that's the concept we're going to be carrying through to guide us. And then also this is important right here. If your radical has a negative inside, do you guys remember what happens when it's a square root and it's negative? The imaginary, right? But if it's a cube root and it's negative, if it's an odd index and you don't have imaginary numbers, you're allowed to have negatives there. Okay? So it's a little bit different. When your index is odd, like a 3 or a 5 or something, you're allowed to have negatives inside, and when you simplify, the negative would just come out of the radical when you're simplifying. It's just when it's an even, like a square root or a fourth root, the negative kind of throws that off. So that's something else to remember about this. That's what I've written right here. Alright, for your support, I have written a list of perfect squares, perfect cubes, and perfect fourth powers for you to reference as we're going through this process. You should have most of these memorized. You should be working on having most of these memorized, and your task is now to memorize these for perfect fourth powers. Those are the ones that we use most often. Alright, so we're going to jump right in. So simplifying radical expressions. I like to split the process into 2 parts. I like to simplify the numerical part first, and then I work with the coefficients second. So the process for simplifying the numbers is to split the number into 2 factors. Factors are numbers that you multiply together in order to get the actual number here. You're going to split it into 2 factors where one of the numbers has to be the biggest perfect power. That would be a factor of that number, and the other one is just the other factor. The reason why I do it that way is so that that number that's the perfect power, if I take the square root or the cube root or the fourth root, whatever it is, of that number, it'll be a whole number that will come outside of the radical. So it just makes I know you guys have probably seen things where, bad example. You guys might have seen things like this. We break it down, you have multiple branches. I don't like that because it gets muddled, and then you guys forget how many of a number to look for to know that it comes outside. I don't like doing that. I like to do it in just 2 branches. I pick the biggest perfect square that's a multiple of 12, which happens to be 4, and then I take the square root of that. 2 on the outside, 3 on the inside. I like it short and sweet and make sure that I understand what's actually going on with the question. So that's the process I'm going to be using throughout the lesson. So let's start over here. The first thing you want to do is make sure you understand which type of root you're working with. I know you guys are really used to doing square root, square root, square root, but you have to remember we're bringing in other types of roots in now too. So you guys, the first thing you want to do is make sure you know what kind of root this is. So we're going to take note, it's a square root. So I'm going to split 45 into two numbers. Because it's a square root, I want one of the numbers to be a perfect square. What two numbers multiply to get 45, or one of them is a perfect square? 9 and 5. I'm going to circle the one that's the perfect power, and I'm going to take the square root of that. What's the square root of 9? 3. So the 3 is going to come outside of the radical to join the negative, so it becomes negative 3. Then I'm going to leave some space, leave some empty space there, and then the 5 stays inside. So the number I circle, I take the square root of that, comes outside, the other number stays on the inside. Now the reason I'm going to leave some space here is because now I have to work with the variables. Some of the variables may come out of the radical too, so you want to leave space for them if you have to write them. Okay? Alright, now the process for variables. There are a couple different ways you can do this. I'm going to describe what's written here, and then I'll show you a visual way that you can do it on the second example. But what I've written here is that you want to take the index, which in this case is a 2. If you feel more comfortable writing the 2 physically, feel free. So the index is 2. What you want to do is consider how many times does the index go into the exponent. So how many 2's can you fit in 2? How many 2's are in 2? 1, right? The answer to that question, when I ask you how many 2's go into 2, your answer is 1. That is the exponent of the variable when it's outside of the radical. So you can write a 1, or you don't have to, because usually exponents of 1 are invisible. Okay, so your answer, there's 1, 2, and 2. If there are any leftovers, if there's a remainder, that would be the power of x on the inside. When I divided 2 into 2, was there any left over? No. So that's why I'm not going to have any x's left inside. So if there are no remainders, if it divides evenly, it's just 2 divided by 2 is 1, and there's nothing left over, then there's nothing left on the inside. If this was a 3 instead, how many 2's are in 3? 1, but then there's 1 left over, right? So then I'd have the x on the inside. So that's the process you can think of in your mind. Another way you can do this, and this gets harder to do the higher your exponent is, but you can do this visually. You can draw little dots for how many x's you have, or whatever number the exponent is, and then you can circle them in groups of whatever the index is, and so there's only one group of 2 and nothing left over. There's a visual way you can do it too. Okay? So this will be your final answer. Alright, let's try the next one. What kind of root is this? Square root. So I want to split 63 into two numbers where one of them is the biggest perfect square possible. 9 and 7. 9 is the perfect square. What's the square root of 9? 3. I'm going to pull the 3 out of the radical. Now, do you guys remember what to do if you already have a number on the outside of the radical and you're pulling another number out? You multiply them. A lot of students get confused on whether it's add or multiply. It's multiply. So if I'm pulling a 3 out to join the 2, I have to multiply them. That gives me a 6. Then I leave some space, and then the 7 is left on the inside. Excuse me. Alright, now I'm going to work with the variables. I have two different variables, y and x. What's the exponent for y? It's a 1. Right? It's invisible, but it's a given that the exponent is 1. How many... Oh, by the way, what's the index for the square root? 2. So you can write that if you want to. How many times does 2 go into 1? None. You can't fit a 2 inside of 1. 1 is too small. So if your exponent is too small, it has to stay on the inside. It wasn't able to simplify out. So because you can't fit any 2's inside of a 1, you can't do it at all. How many 2's can you fit inside of 11? 5. So that means you're going to have x to the 5 on the outside. But did you have any left over from the 11 after you took out? How many? 1. So you're going to have x to the 1 on the inside. And then the visual, you could do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 dots. And then circle them in pairs. So I have 1, 2, 3, 4, 5, 5, and 1 left over. So that's a visual. Okay? So that would be your final answer. Alright, next one, we have another square root, so I need a perfect square that is a factor of 98. Biggest perfect square possible. If you're not sure, you just want to start dividing 98 by square root, or perfect squares until you get to the biggest one that works. Or, yeah, start dividing it by perfect squares. 47 and 2. Oh, sorry, 49. 49 and 2, because the square root is 7. So it's 49 and 2. Maybe you'll get there eventually. You start dividing by 4, then 9, then 25, 16, all those. You'll get up to 49, and you'll get it. So I'm going to take the square root of 49, and what does that give me? 7. So I'm going to be pulling out a 7, but there's already a 5 there. So 5 times 7, which gives me 35. Leave some space. And then the other number, the 2, stays on the inside. Okay? Now the variables. What is the index for this?
2.
An index of 2. How many times does 2 go into 20? 10.
What about the bees?
Oh, sorry. Forget the P. That's not supposed to be there.
Oh.
You can just scribble it out from the question. Sorry. Sorry, that's a 10. My hand already got smushed. Alright, so there are 10 2s and 20. Were there any left over? No, so there's nothing, there are no A's left over in here. They all simplify out. How many times does 2 go into 3? Once. So B to the 1 comes on the outside. Is there any left over from the 3 when you take out one of the 2's? How many? So B to the 1. Alright, you guys see how we're doing that? Next row. Alright, now I'm going to stop at the square roots. I'm going to bring in the other types of roots now. So this one is a cube root. So when we split into two numbers, I need you guys to find a perfect cube. We need the type of number to match the index. So because this is a cube root, I need a perfect cube that is a factor of 56. 8 and 7. Which one of those is a perfect cube? 8. So then what is the cube root of 8? 2. The 2 is going to come out to join the negative 4. Excuse me. Negative 8. Leave some space. You have your 7. Please make sure when you notice that it's a cube root, please make sure you're continuing to write the little index here to indicate it's a cube root. I know it's really easy to forget that and just write square root because we're so used to that. Please make sure you're paying attention to the details. Alright, now the variables. The index is 3. How many times does 3 go into 2?
0.
None. The 2 is too small, so it's stuck inside. Okay? How many 3's can you fit into 8? 2. So I have y to the 2, that's 6, right? Now if you take 6 away from the 8, how many are left?
2.
So you have y2 on the inside as well. The quotient is on the outside, the remainder is on the inside. Alright, next one. Now, this one you guys need to pay extra close attention. See how there's a negative there? Is it okay that we have a negative there? Because it's a cube root. The index is odd, so that means we're okay with the negative. It just means that when you guys split this number, because it's a cube root, I need a perfect cube, and the perfect cube needs to be negative. So you're going to attach the negative to the cube root, so when it simplifies, it'll come out. Alright, so what's a perfect cube? You guys have a list up there. What's a perfect cube that is a factor of negative 135? Negative 27. What's the other number? 5. Alright, so again, you want to attach the negative to the 27, not the 5. Because now we're going to take the cube root of negative 27.
3.
What's the cube root of negative 27? Negative 3. Because negative 3 times negative 3 times negative 3 gives you that negative 27. So I'm going to have a negative 3 on the outside and a positive 5 on the inside. That's the whole point. You want the negative to come out. So make sure that when you guys are taking the cube root of something that's negative, the negative comes out when you simplify. Alright, everybody good so far? Alright, now the variables. The index is 3. How many times does 3 go into 5? Once. You can only fit 3 and 5 once. And then how many is left over of the 5 when you take the 3? 2. Again, you have 1, 2, 3, 4, 5. One group of 3, 2 left over. Okay. Alright, and then how many times does 3 go into 3? Once. How many left over? So there are no more y's on the inside. They all simplify out. Alright, questions? Alright, here's our last one. This is now my 4th root. Alright. We usually don't go much higher than 4th roots, but you might still see them. So I need a perfect fourth power that is a factor of 128. 16. So if you look at the list that I have for you, the perfect fourth powers are 1681, 256, and 625. So 16 is a factor of 128. You can just really quickly divide by 16, you get the 8. You can see that they're kind of factors. What do you think the fourth root of 16 would be?
2.
It's 2. 2 times 2 times 2 times 2. So the 2 comes outside to join the 7, giving me 14. And 8. Again, don't forget to write your index of 4. This is a fourth root. Don't forget the index. Alright, now the variables. The index is 4. How many 4s are in 6?
1.
Only 1. Okay. So if I take the 4 away from the 6, how many are left?
2.
2. So I have h squared on the inside. Right? How many 4s are in 8?
2.
2. How many left over?
0.
Right, how many 4s go into 8 again for the k?
2.
2. Nothing left over. Now one quick thing before I move on from this. This is usually the hardest unit for me to grade because of people's handwriting. So if you guys would be really nice to me, see how we have all these powers here kind of pushed up close to the index? When you have powers and an index right next to each other, it gets really hard for me to tell the difference between the two. So when you guys are writing your roots, if you could put your index as close to the inside of the corner as possible, that will help me tell the difference between that and any powers that are attached to a variable next to it. Okay? So try to write as neatly as possible so I can tell the difference. Alright, any questions on simplifying? Okay. Then we're going to multiply radicals. Multiplying radicals is very simple. All you need to do is make sure that the indices are the same. You can't multiply a square root times a cube root or a cube root times a fourth root. They have to be the same type of root in order to multiply them together. Once you've confirmed that they are the same, all you have to do is multiply the outsides together. Whatever's on the outside gets multiplied, whatever is on the inside gets multiplied, and then you simplify if you can. It's really straightforward. Okay? So like for this one, the two numbers that are on the outside are 2 and 3, so you would multiply them together to get 6. The two numbers on the inside of the square root are 5 and 7, you would multiply them together to get 35. At this point, once it's now one radical, you ask yourself, can I simplify that? Can I split 35 into 2 factors where one of them is a perfect square? Is that possible? What are the 2 factors of 35? 5 and 7, neither of which are perfect squares, so that would be my answer. Okay. Next up, again on the outside we have 4 and 3. That multiplies to get 12. This is a cube root this time, so don't forget your index. 6 times 12 is 72. So that's the multiplication part done, and that's great. But you need to make sure that your final answer is fully simplified. Can I simplify the cube root of 72?
Yes.
Yes. I'm going to split 72 into 2 numbers, 2 factors.
7.
Okay. Am I going to be focusing more on the 8 or the 9? 8. Because remember, this is a cube root, so I want the perfect cube. I understand 9 is a perfect square, but that's not relevant here. I want the perfect cube. So what is the cube root of 8?
2.
Comes out to join the 12, gives me
24.
leaving just the cube root of 9. You see, we did the simplifying first. You guys had an understanding of that before we did multiplication, because multiplication does involve simplifying at the end. Alright, this one, we have 2, that's really smeared on the board, fifth roots, okay? So we're going to multiply them together. There's nothing on the outside to multiply, so I'm just going to go straight for the inside. That gives me negative 32. Now, is there a problem with the negative in this scenario?
No.
No, because
It's an odd one.
because the index is odd, so it's fine. Now, I know I only have a list for up to the perfect fourth powers. When you guys are here, do you know how to do high powers in your calculator? Or sorry, high roots. When you guys get something like this and you're trying to figure out what the perfect powers of 5 are, you could obviously just do like 2 to the 5th power, 3 to the 5th power, 4 to the 5th power, and find out what those numbers are. Or you guys could actually put this in your calculator. Now the way you do that, if you have a TI-83, I don't know if it's different on an 84, But if you have an 83, you would type down what the index is, so you would type 5, and then hit math 5, and then type in the radicand, which is negative 32, and it would give you the result.
Yeah, it's this one.
So what is the result? So what's nice about this is that negative 32 is, in and of itself, a perfect fifth power. So you don't have to do the whole split thing. You just have to check, oh, I don't know about that, but I'll check really quick in my calculator, and if it comes out as a whole number, it was already a perfect fifth power. If it doesn't come out as a whole number, like it gives you a decimal or something, that means you would have to try to split it to simplify. Okay? Okay. Next up, this guy right here. 2 square roots, so I can multiply them. So if I multiply the insides, what would I get? For which one? Okay. Well,
What do you mean the X left?
oops. There's an X right here. Okay, that's fine. Okay, so that means that there's still an X on the outside. And then when I multiply the insides, what do I get? 36. X to the fifth power. Hopefully you guys remember that when you multiply the same variables together, the exponents add. If I remember that right. Alright, so that's just the multiplication part. Now once I have it as one radical, I need to simplify. So because this is a square root, what do I know about 36? Square. So what would the square root of that be? 6. So I have 6x. No number left on the inside anymore. And then I have x to the 5. So what's the index for this again? 2. How many 2's can you fit in 5? 2. Now here's the kicker. I already have an x on the outside. If I'm bringing 2 more out, what's the cumulative power? X to the third. If you already have something on the outside that's a variable and you're bringing more out, you just add onto the exponent that's there. And then if I pulled out, so that was 4, right? So then how many do I have left over? 1. So like that. Because, see how this x is already here? How many, so we said that there were 2 2's in 5, correct? So I was going to pull out x squared. But I already had an x.
Oh, yeah.
So it was like that, and then it combines to become x squared. Okay. Alright, what about this middle one? They don't have the same index. This is a 7th root, this is a 5th root, so can I multiply them? You won't see this a lot, but I put it here just in case. Always make sure you double check to make sure they're the same root. If they're not the same root, you can't do it. These ones, no, they have to be identical to each other. Same type of root. These ones are the same root, so I'm going to go ahead and multiply those. So I'm going to get a relatively large number from multiplying those. 1575. And then again, when you multiply with the variables, the exponents add. So I'm going to x to the 6, y to the 7. Is everybody with me up to there? Cool. Alright, now I need to split. It is a big number, so you guys are going to have to think strategically. Maybe the perfect square you're going to be focusing on is one of the bigger ones. So I'm going to start there. You're going to take forever. Nope, 25 is not the biggest one. If there's another perfect, so if you did 25 and 63, there's another perfect square inside of 63. So that means 25 was the big one. So keep going. The biggest perfect square possible. Mm-hmm. 225 and 7. 225 and 7. So 225 is the biggest perfect square that's a factor of 1,575. What is the square root of that?
15.
So I have 15 on the outside and then the 7 on the inside. I'm going to work through the exponents. So my index is a 2. How many 2's are in 6? So what would I have on the outside? That's 3. How many 2's do I have in 7? 3 again. But that counts for 6. So I have 1 left over. I can get y1 on the inside. Okay. Any questions about that? Cool. Great. The last main thing we're going to talk about today is dividing. So for dividing radical expressions, there are 2 different scenarios. There's a scenario, I like to call them the full house and the split house. So we have the one on the left where it's one big radical with the entire fraction inside of just the one radical. And then we have this one where it's 2 radicals separate with the division sign in between them. So I call this full house, split house. So the numbers and the variables determine which one of these you should write them as, or which form you should use. So you're going to use this one if the numbers that you're dividing divide evenly. So something like 10 and 2, or 8 and 4. Stuff like that. That will divide evenly without giving you a decimal. As well as the variables, if you have variables, the exponent on the top has to be higher. So if you have those 2 things, that's written here, then you would write it as a full house. However, if the numbers do not divide evenly, like 7 divided by 5, or 10 divided by 6, right? They don't divide evenly just to give you a nice clean round number. If that's the case, or the exponent on the bottom is bigger than on the top, you guys would have to write it as a split house. Okay? If you are in the full house scenario, all you have to do is simplify the fraction. This is actually really nice because the fraction will go away. So like if you have 10 divided by 2, that just becomes 5. No more fraction. So that will happen here. The fraction will go away and then you just simplify it like normal. However, for this one, it takes a little bit more work. You have to simplify the top radical, then simplify the bottom radical, and then try to cancel anything that they have in common afterwards. Okay? So that's the 2 different possibilities. What's annoying though is that when they give you the question, when they print it for you, they may not have written it in the correct format. So you have to check and maybe rewrite it. So if we're looking at this one right here, I have 18 divided by 1, really. Does 18 divide by 1 divide cleanly? Okay. Is the higher power on top? So, should I write this as a full house or a split house? Split. So this is fine. We're good to go. So the first thing I'm going to do is simplify. Oops, I should not do that. I'm going to simplify the top radical. Okay? So, because it's a square root, I'm going to split 18 into 2 numbers where one of them is a perfect square. So what 2 numbers would I use? 9 and 2. 9 is the perfect square. Take the square root of that. What comes outside of the radical? 3. 3 on the outside, 2 on the inside. What's the index for this again? 2. How many 2's go into 4?
2.
With how many left over? Okay, so that's the top radical, simplified. Now I have to start all over and simplify the bottom one. The bottom one doesn't have any numbers, it only has variables. So the index is 2. By the way, the indices have to be the same to divide, just like they were to multiply. So the index is 2. So how many 2's are in 6?
3.
So this becomes x to the 3 with nothing left over, so the radical completely simplifies away. No more radical. Once you're here, your next job is to simplify the fraction by crossing out anything that they have in common top bottom. So is there anything that you can divide away from the top and the bottom? Think kind of like factoring. What do both of them have in common that you can divide away? X squared. I can take this x squared away, and I can take this x, I can take an x squared away from that, leaving me with just an x, right? So my final answer would be 3 square root of 2 over x. So think of it in the context of factoring. You're dividing away something that they have in common. Alright, this next one, we need to see if this is written correctly, because if it's not, we're not going to be able to move forward. So, are these 2 numbers, can they divide evenly? The 49 divided by 25? Okay, so should I have written this as a full house or a split house? So this is written incorrectly. If it is written incorrectly, you guys need to change it so that it is written in the appropriate form. Like I said, they may start off in the wrong format. So I have to fix it. Now, again, with the split house format, you have to simplify the top and then simplify the bottom and then cancel out things that they have in common. So, what do I know about 49?
It's a perfect.
It is a perfect square by itself. So what's the square root of 47? Sorry, 49. 7. So I have 7 on the outside, and there's nothing left over because 49 was a perfect square in and of itself. Alright, the index of this is 2. Remember, the square root has an index of 2. How many 2's fit in 3?
2.
Only 1. There's only one x. Or sorry, only 1, 2, and 3. How many was left over when you take the 2 away? So you still have 1 left over. Again, if you guys need to, you can do the dots and then circle 2 of them. You have one group of 2 and 1 left over. Again, you can use a visual if you need to. Alright, what about the bottom? What do I know about 25?
Perfect cube.
Perfect square. So I have 5 on the outside and nothing left on the inside in terms of numbers. The index is 2. How many 2's go into 4?
2.
With how many left over?
0.
So I just have y squared. No more radical. Everything that was in the radical simplified out neatly with nothing left over. So no more radical. Alright, is there anything in common top bottom that I can cancel? No. So that would be my time. You don't always have to cancel something. Look for it, but it won't always be the case that you do. Alright. 2 more. What about this one? Does 189 divide evenly with 7?
Yes.
Yes, okay. Is the higher exponent on top? Okay, so should I write it in the full house format or the split house? So it's written correctly, right? Alright, so this one's nice because what I'm going to do is I'm going to simplify the fraction first. So what is 189 divided by 7?
27.
And then when I have x to the 7 divided by x squared, you subtract. So if I had 7 on top, 2 on bottom, and I divide, I'm going to subtract them. X to the 5th power. Now that I don't have a fraction anymore, I would just simplify this like we did in the first section. Okay? What do I know about 27?
It's a perfect cube.
It is a perfect cube. Okay? So if it's already a perfect cube by itself, I just take the cube root of that. What is the cube root of 27?
2.
Okay, so I don't have a number left inside of the radical, but now I have to work with the variable. So how many times does 3 go into 5?
Once.
Only once. So I only have one x on the outside. But if I have that one group of 3, how many is left over? 2. Because there's not a fraction, there's nothing else to cancel, so I just leave it like that. Okay? Last one. Does 32 divide evenly with 27? So should I have it written like this, or should I switch it to the full house?
It's written.
It's written correctly. Right? Remember when these two numbers split, they have their own unique radical. Alright. How would I know that 32 in and of itself is not a perfect cube, so I'm going to have to split it. So what two numbers would I use? 16 and 2?
8 and 2.
Would I use 16 and 2? Why not? 16 is a perfect square.
But it's not a perfect
This
cube.
is a cube root. Again, make sure you're paying attention. So I want a perfect cube, so that would be, what is it, 8 and 4? Okay, so 8 is a perfect cube. The cube root of that is 2. So I have a 2 on the outside, keeps some space, and then the 4 stays on the inside. The index is 3. How many times can you put 3 into 5? Once. With how many left over?
2.
2. Again, 1, 2, 3, 4, 5. One group of 3, 2 left over. Alright, same thing with the y's. Different variable, but the exact same scenario. Then we switch to the bottom. We already talked about 27. It is a perfect cube. So it becomes 3 on the outside, and then there is no number left over on the inside. It's simplified out all the way. If the index is 3, how many times does 3 go into 3? Once, with no left over, so no more x's. And then how many times does 3 go into 6?
2.
With how many left over?
2.
None. So I can actually erase this. You don't need that. You can write it if you want to, but if it's empty, you don't need it there anymore, so you should erase it so it doesn't confuse you. Alright, is there anything I can cancel out? Top, bottom.
The x and the
I can
y.
cancel out the x,
And the y.
and then one y. The bottom had y squared, which is really 2 y's, and the top had only 1. So now the top is going to be 2 cube roots of 4x squared y squared over 3y. Now, quick note, anything that's inside of the radical, you cannot cancel that away with anything that's outside of the radical. So don't try to cancel this x squared with that x. Okay, you have to all be outside of the radical to cancel. Alright, that's the primary idea of what we were going to talk about with this lesson. Does anybody guess?
Where did you get the 3 again? What's the denominator?
So I took the cube root of 27. Any other questions? Alright, the last thing we're going to talk about is this idea of rationalizing the denominator. Yes? No, there's the y on the top and the y squared on the bottom.
So what if like the bottom also has a square root, like and you can simplify, so you remove that?
You can only cancel out actual radical expressions if they're identical to each other. So if you had like radical 2x y over radical 2x, you can't just cancel out the 2x parts of the radical y. They have to be identical to each other in order to cancel. Alright, so the last thing we're going to talk about really briefly is rationalizing the denominator. You guys would have seen this also very briefly in geometry when you guys were talking about special right triangles. It is not an emphasis in Algebra 2, but it is still something I need to tell you guys about or remind you. So I have a really cool, easy shortcut trick thing for when it's a square root, but when it's a cube root or higher, it gets a little bit more complicated. So these first two are where you guys can, so I've described the process in general here, and then the shortcut, that's what I'm going to use for the first two examples. So the shortcut is if you guys are working with square roots, all you have to do is take the radical that's in the denominator and move it to the top. So instead of being the bottom, it would be in the top, but you still have to have something in the denominator. So instead of radical 3, you're just going to leave the 3, the radicand. Okay? So you take the radical expression, move it to the top, and then leave the radicand behind without the actual symbol. And that's what it would look like. The reason why we rationalize the denominator is because it's improper to write a fraction with a radical in the denominator. So that's why we have to rewrite it in a different format. So this would be the same number as that. You can test it in your calculator if you want to, but those two numbers are the same. Same thing for this. I would shift the radical 4y to the top and just leave 4y without the radical in the bottom. But what's different about this scenario is that I will have to neaten it up a little bit. It's a little bit sloppy. I'm going to need to simplify it as much as I can. So what's something I could do to simplify the top? The 4, right? This is square root of 4y. Do I know what the square root of 4 is?
Yes.
What is it?
2.
2. So I can pull out a 2 to really get 4x radical y. The y doesn't simplify out. And then what does the bottom become when I multiply all that together?
4y squared.
Okay? And then there's one more thing I can do to simplify it even more.
Divide by 4.
Cancel, cancel. So I get x through y over y squared. So even when you rationalize, you will be fundamentally changing how the fraction appears, and you may have to do some steps to simplify it, but the actual shortcut shouldn't be that hard to actually do. Now the very last example here is not a square root anymore, so we can't do that little shortcut I was talking about. What you need to do instead is think strategically. If I don't want the radical in the denominator anymore, I'm going to have to change the number inside of the radical to something that will simplify. Okay? So I already know that you can't take the cube root of 4, but what is the number you can take a cube root of? 8, for example. Okay? So I need to figure out how to change the 4 to an 8.
4 times 2.
You would multiply times 2. So I'm going to multiply the denominator by the cube root of 2. Remember, you can only change a number inside if you multiply it times the same root. So I'm going to multiply the denominator by the cube root of 2 to make it the cube root of 8. Because I know that will simplify easily. But I have to make sure that the fraction stays the same. So anything I do at the bottom, I have to do at the top. So then that would be the cube root of 2x. Then all you have to do is actually do the cube root of 8, which is 2. And that would be the rationalized form. So again, this one where it's not a square root and you can use this really cool trick thingy, You have to think strategically. You have to force whatever's inside of the radical to be something that can simplify. Whatever it is you need to multiply by, you do that top and bottom and then simplify. Okay.
Is that a 3 on the top?
Sorry?
Is that a 3 on the top?
Cube root of 2x.